Okay, so so far we have derived the velocity profile, and also we have found out the expressions for average and maximum velocity, and also we cast the velocity profile, that is the UR, in terms of the average and maximum velocity as well. And also we found out the pressure drop formula delta P, and now the next thing is that to find out the Darcy friction factor, that is the F. And this Darcy friction factor basically denotes the head loss due to friction, that is also known as HF. And there are two types, the major and the minor, so I will not go into this discussion. So let's dive into directly into the Darcy's friction factor and also coefficient of friction. So I will discuss them one by one. So we can define the Darcy's friction factor as the dimensionless quantity used in Darcy Weisbach equation for the description of friction losses in pipe flow as well as open channel flow. It is also known as the Darcy Weisbach friction factor or Moody's friction factor, as you can see in the Moody's diagram, and it is 4 times larger than the Fanning friction factor. I'll discuss this thing in the next video, and this is the coefficient of friction, and that we define by the ratio of wall shear stress divided by 1 upon 2 rho A rho V square. Let me confirm this expression, areas there are not. So, but this is like a friction factor. This is the coefficient of friction, and this is like a 1 by 4th, or friction factor is 4 times of CF. So this we will see in the next video. And the formula for the pressure drop. So basically, this is we are continuing with the same thing, that is the pressure drop, but we want to cast this formula in a different form, that is in the terms of the friction factor. And why I want to do this thing? Because the friction factor, we have the diagram or the Moody's chart, and in this diagram we have the 2 sections. In fact, there are 3 sections. One is for laminar flow and one for the transition flow. In the laminar flow with the Reynolds number, the friction factor is decreasing, but that is opposite in the case of transitional flow, that can go up to some Reynolds number, and that is, I think, up to the 10 power 4000. Okay, and after that the laminar flow, turbulent flow will be there, and there are the 2 things we can see here. One is the case when the pipe is smooth, and then we have the friction or the roughnesses on the pipe surface, and here we have the relative roughness, that is the roughness divided by diameter. And so you can take the Reynolds number, and then you can get the relative roughness factor, and then you can find out the friction factor. Same thing you can also do in the case of laminar flow, but you don't require any roughness factor. And the slope here is 64 upon Reynolds number. I will discuss this thing later on. So right now we are talking about this formula of pressure loss in terms of friction factor, and also what should be the expression for the friction factor. So we start from this formula, which is for delta P, or pressure loss, and also we know that the velocity profile in terms of average velocity is like this. So now let's draw the pipe section. And this is the velocity profile. Maximum velocity is on the center. And on the wall, we have the wall shear stress. So basically, the wall shear stress will be everywhere, but like here, the shear stress diagram will be look like this, because this is 0 at the center, where the slope of velocity is equal to 0, and it's a maximum on the wall, which we call the wall shear stress, and the formula for the shear stress is minus, that is to make the sign positive for the, because the velocity gradient will be negative, so make it positive quantity, we put the minus sign, and partial u by partial r at okay. So this is about the simple shear stress. And when we write down the wall shear stress, that is the tau wall, this becomes the slightly different. This will be minus mu partial u by partial r, but when r is equal to r, capital R. And this is happening here. So in the center, the r is equal to 0, and here the r is equal to capital R. So we know that we have to find out the velocity gradient and then put the r is equal to r and then multiply with the minus mu, we get the velocity profile. We will get the wall shear stress. So first you can write down this du by dr because it's a single variable. So you can also make the partial derivative as a simple derivative. So this becomes the 2u average 0 minus 2r upon r square. So this becomes the minus 4 times the u average and r upon r square. So if you want to find out the velocity gradient at the wall, so this becomes the du by dr at the r is equal to r. So this becomes minus 4 u average. This will become the capital R. So r upon r square. So one r will be in the numerator, in the denominator, and we get the expression as minus 4 u average divided by r. And as I mentioned earlier that the formula for wall shear stress is equal to minus mu du by dr, or simply our partial derivative of u with respect to r, where r is equal to r. So put the values here, minus mu, and then we have the minus 4 u average divided by r. Okay, so this becomes the minus will be a positive sign. So 4 mu u average upon r. So if I change the r to the diameter, this will be the d by 2, and we will get the, so d by 2, this r is the d by 2. So 2 will be in the numerator, then this will become the 8 mu u average and divided by diameter. Okay, so now we found out the value for the wall shear stress. So you can copy this and place over here. Okay, so one thing I want to clarify that the actual derivation that you can get for the friction factor or the head loss using the momentum balance. So with the momentum balance, you can directly get this equation. But I was interested to find out that how we get these relationship from the in this sequence. So that's why I followed the one book. That book can be the Munson's or can be the Frank M. White. So I wanted to see that how these formulas come up from these expressions side by side. Okay, so instead of going to the basic principle, I wanted to see that how we can derive the one thing from second thing, okay, or second thing from the first thing. So now what you have to do is that you have to write down the delta P here. So 32 mu length and u average and divided by d square. Okay, so I will now separate them in this form. So number one is that we have the like the density times the U average square upon 2. Second term will be the L by D. L by D is very important term. So the remaining things we have is so when 2 is taken common, the 32 will become the 64. 64 is there, and we have not taken the viscosity common, so mu will remain there, and L already is inside, so this L will be not will be written here, and the 1D is already taken there, so this single D will be remaining here, and because there was only one U average, and we have taken common as a U average square, so we have to write down the U average, one U average here also. So I think if you compare, this will become the, so U average is there, L is here, mu is here, D square is here, and 32 also here. So you can make them close to each other like this. Okay, so the next thing is that now we know that the wall shear stress formula is 8 mu U average upon D. So now let's write down 64 as the 8. Okay, and also write down the mu and U average, and divided by D. This is the equal to wall shear stress. So the remaining terms from this expression, they will become, so we have taken the 8 common, so 8 will be there from 64. We have taken the mu common, so mu will be there, and also in this expression we have taken the density common. The density should be here also in this formula. So now from this term, 8 is here, viscosity is in the first term. So in numerator we have only 8, and in the denominator we are going to have the density, but diameter already is inside, so we have to know we have the 1 here, and there was a U average, but U average are now is in the numerator, so this will be the U average square. So you can see that this is something like a same term we are getting here, and then write down the L by D same, and also rho U average square upon 8. So now I can write down this thing. This thing is a wall shear stress. This is the 8 upon rho U average square. Then we have the L by D, and then we have the U density times the velocity average square upon 8. It should be the 2. Okay, so we can write down this thing as, this is the delta P. So we can write down this expression as 8 times the wall shear stress divided by density U average square. So you can see that we have this term, that is the 8 wall shear stress divided by rho V average square. The second term is going to be the same term, that is the L by D. And the third term is the 1 upon 2 rho U average square upon 2. So now I can write down the this wall shear stress delta P as the friction factor, and then L by D, and then the density times the velocity average square upon 2. This is a formula which we required, okay? And the friction factor is equal to A times the wall shear stress divided by rho U average square. And the wall shear stress in terms of the after the derivation, this is equal to 8 mu U average divided by D. So now we have these three expressions. They will basically will complement each other. Definitely, when you want to find out the fraction factor from the directly from the formula, you will need this formula. But for this formula, you need the these terms, because the wall shear stress you can find out, but instead of finding out them again from the basic principles, why not to use the equation which is given here? Okay. So now we have our new formulas. These are the set of 3 equations, and we can find out the delta P are the pressure loss because of friction from these formulas. But definitely, I would recommend that to find out the fraction factor, it's much easier to use this formula and use this chart. And then the L by D is a known quantity, density is known quantity, and every velocity, that is the velocity at the inlet, also known quantity, and the remaining terms are the constant values.